Hello and welcome back to a course on set theory, logic, and inference. We've spent the last couple of lectures giving some context and motivation for why we should study this material, and now we're ready to dive into talking about set theory. So let's get started. First, we need some definitions, and the first definition we need is, what is a definition? So the notion of a definition is that it's an accurate description of some sort of object or concept. And definitions can be either simple or possibly very complex, but most importantly, they must be precise. It must be clear what objects or concepts are being described. What are we talking about, and how is it different from all the other things that it might be confused with? This is a notion that philosophers call differentia. What differentiates a notion from other notions? There is also often an intuition behind a definition. The definition attempts to describe some sort of real concept that presumably people have an idea about what it is. And we're trying to communicate that idea to other people and do it in a way that's as formal as possible so that we don't have confusion. Of course, this background, this intuition could be dangerous, right? Because if you're really purporting to have a formal definition of something, then the definition is just in the mathematics or in the semi-formal natural language description that you're providing. And so if there's an intuition that's outside that, technically that's not part of the definition. The intuition is just what you have in your head that motivates you or helps you to create the formal definition. And the more that you can eliminate resorting to an intuition that's behind the concept and make it instead explicit, the better a definition it will be. There are also differences between different sorts of definitions. In mathematics, one normally has necessary and sufficient definitions. We can talk about all of the criteria or qualities that must be present for identifying a particular object or concept. And it's also usually the case that once having done that enumeration of all the essential properties, there isn't anything else left. It's sufficient. To say anything else would be redundant. Now, this is not true for definitions that we might get in a lot of real-world human common sense notions. The notion of what it is to be a walking or a talking or something of that sort may well have a set of necessary conditions, but not a set of sufficient conditions. But if we're in mathematics, we're talking about something like the definition of a right triangle. Well, a right triangle is a triangle that has one right angle. And there's nothing else that you need to say in order to define that concept. Anything else would be superfluous or redundant. We're also going to need to define this notion of proof. This is really central to this entire course, this entire exercise. We need to be able to have a notion of how we actually prove something to one another. And a proof, historically could be at least semi-formal. Now that we have available software and systems that can verify what we're saying algorithmically, really objectively, knowing that there is no human intuition behind it. We're just running a mathematical process. It's clear that the whole field of mathematics is moving towards an ever greater rigor, and we talked about Russell and Whitehead's attempt to do that in a really exhaustive way for mathematics. That was really, I think, an inflection point in the field. So what is a proof? A proof is an argument that convinces a reasonable and unbiased recipient of the undeniable truth of a statement. And if we can do that purely mechanically, I think we have an even higher level of trust or verification in this notion of proof. Okay. And proof is almost always conditional. It relies upon some premises. So if we want to say prove one triangle is identical to another triangle, there are going to be some premises like those triangles share two identical angles. So the conclusion we reach is with respect to the assumptions. Now, if we're doing an informal proof, there may be some things that we just assume everybody knows and agrees on, but it's much better if we can be explicit about those things. If we're doing a formal proof on a machine running an algorithm, we have no choice other than to be completely explicit about those assumptions, unless they're sort of built into the mathematics already. Right, so they're often implicit for semi-formal proofs, often explicit for really, really formal proofs. So we might assume, for example, in an informal proof, especially if humans were communicating to one another, that we all know what the natural numbers are, we all know the meaning of certain symbols. Set theory as a discipline is usually attributed to George Cantor, who had the following quote: "By a set, we mean any combination M of a certain well-distinguished objects in our intuition or our thinking, which are called the elements of M, into a whole." So interesting that even at the start of set theory, there was this notion of we might have an intuition or a thought about how things could in a set could be identified, and this just got more formal over time. So what's the definition of a set? A more modern definition of a set: it's a collection of objects viewed as a unit or a group, a group of things taken together. The objects are called the elements of a set. And elements can be any sort of object. They could be numbers, words, other sets. This is a particularly interesting case. You can have sets of sets or sets of sets of sets and so on. We might also have sets of lists, sets of pairs, sets of functions, and we might also be talking about sets of real-world things, not just abstractions in mathematics. We might talk about a set of people, a set of vehicles, a set of courses that are being taught, for example. The set of all currently considered objects, when we're doing set theory, is often called the universe or the domain or the carrier set. It's the possible things that the elements of this set are taken from. So if we're doing sets about the natural numbers, then the carrier set or the universe is the set of all natural numbers. And then we can start to describe sets that are smaller than the set of all natural numbers. The set 2, 3, 4, for example, is taken from this universe. It's a set that has elements that are taken from the universe. And I also want to bring in this notion of ontology or categories. So people naturally create categories to help understand their world, and mathematics is also a process of creating formalizations and abstractions that help us describe our world in a more precise way, in a way that gets closer and closer to being something mechanical. And this is particularly true in the last few decades now, that we do have machines that can manipulate formal languages and give us proofs for things. Even the most primitive early humans certainly had some kind of categories for the set of things that could be eaten or the set of things that could be burned for warmth. A baby, a toddler, will certainly have categories about things it can eat, things it doesn't like, things it can put in its mouth. The notion of creating categories is sort of inherent in human existence. And for adult humans in the modern world, well, we all naturally create categories as well. This doesn't stop in childhood. It didn't stop at primitive times. If we're going to buy a car, we might have a notion of the set of all cars on a used car lot that are fun to drive, and the set of all cars on the lot that we can afford. And we sure hope as a car buyer that we can have an intersection between those two sets. And we might say that the universe that we care about in that case is the set of all cars on the used car lot. So set theory is an abstraction that helps us in theorem proving. It helps us to describe the world. It helps us to make systems that can tell us interesting things about the world by following mechanized mathematical procedures. And we want systems ultimately, I believe, that help us make some of the same inferences about the world that people do. That's the value of these mathematical abstractions, right? They have predictive value. If you create a system that is mechanizable, and you follow the mechanical rules of the system, you can do computations on paper or on a chalkboard or in a machine that make a prediction about the world. You're working in a sort of simplified, abstracted system that you can take, say, a word problem, a high school word problem about a train traveling on the tracks over a specific time, and maybe you want to make a prediction about when that train arrives at its destination. So you create an abstraction from the word problem that is some very simple arithmetic. You do the problem in the arithmetic, and then that makes a prediction that you can take from that abstraction back into the real world. A useful mathematics, or any kind of useful science really, is one that creates an abstraction and then makes a prediction that is useful in the real world, at least to some degree. So continuing with our definition of a set, we can have an explicit enumeration of a set. So for example, the set A, 2, 3, 5, 7, 11, 13, we've said those are the members of that set and no other. We can also give a sort of a pattern. We can say that the natural numbers are 0, 1, 2, 3, and so on. We're using this notion often common in mathematics called induction in this case. We're saying, here's a pattern, and the pattern continues. Right? We've shown you the pattern, and you should be able to extrapolate, or a machine should be able to extrapolate what all the other values are. And here we don't want to enumerate all the values because we can't. The set of all natural numbers is infinite. So we just give a pattern. However, a quick note, there are different opinions about whether the natural numbers should include 0. Most commonly nowadays it seems to in the literature, and so that's what I'm going to stick with, that n, the set of all natural numbers, is the set of positive numbers. We can also describe sets with a descriptive form, maybe some sort of algorithm really. So we could say that the set A is all x, where x is prime and x is less than or equal to 13. Right? So 2, 3, 5, 7, 11, and 13 are all prime numbers, and they're all less than or equal to 13. We can also give individual members. Maybe we're building up a set over time, over the course of a discussion, and we can say 2 is an element of set A, 2 is in A, 2 is an element of A, 2 is a member of A. These are all synonyms. We can also say something is not in A. Usually the notation there is to have this funny E-looking symbol and just draw a line through it. So throughout this course there is a certain amount of terminology. I'm going to try to highlight that terminology and come back to it to reinforce it. But just be aware that, like for any sort of mathematical discipline, there is a certain amount of symbology that one has to learn and get conversant with in order to be comfortable doing work in this area. But one thing I also want to do in this course throughout is whenever we do something in math, that we also want to do it in programming. This is a course for programmers, for computer scientists. So let's take a look at how some of these mathematical notions can be expressed in a popular programming language, in Python. You can certainly do this in other languages, but because Python is so popular these days, that's what I'm going to stick with. So let's try to replicate these notions. Sets are a data type. We can create a set and print it to verify that we've done things correctly, and we can also test for set membership. So here, if we define the examples that we had on the previous slide, so my set equals 2, 3, 5, 7, 11, 13, we can print it. We can also print whether something is an element of the set. We can also get a false answer, or an answer of false, when we ask to print something being in the set that is not in the set. So just as an exercise, we're going to have a couple of really, really tiny and hopefully trivial exercises, but I think it's really good to develop the muscle memory of writing these things yourself in Python as we go along. So the next few slides, and really throughout this course, there's going to be some simple exercises and some complicated exercises. Here initially, these are quite simple. And I just suggest that you do them. They'll only take you a moment, and I believe, it certainly has been the case in my experience, when you type something in like this, you take just a moment, but it's kind of cements it in your memory. It's kind of a way to have multimodal learning. I should also say that with regard to the MIU problem, some of you may still be doing that problem, and you've got a choice here, or maybe your instructor has a choice about whether you might want to do that work in parallel with these new exercises, or whether you want to do it sequentially. So one option is to just exhaust the work that you want to do on MIU, including the extra credit, and before you go on to this, but you could also do it in parallel just fine. We won't get into anything that depends upon the learning that happens in the MIU problem until much later in this series. All right, so as an exercise, I'd suggest just try to print out whether 6 and 7 are in my set. In terms of descriptions, great, because we talked about that sets can be defined by an exhaustive enumeration of their members or a description or a pattern. We don't exactly have the same notation in Python, but we can always just write a little program. So let's say that we have a list object. We'll use the list as though it was a set for the time being to avoid getting into any more different data structures. Everybody in Python certainly is familiar with lists. And so let's just say that we'll have an iterator. It goes looking through the numbers from 1 to 20. And if it's an even number, then we'll put that into this list, and then we'll turn the list into a set just in case we screwed up and we had some duplicates in our list. Right? So this is kind of maybe it's a little convoluted, but hopefully it's easy to follow. So we're creating the set of all even numbers less than or equal to 18, or all the set of all even numbers less than 20 would be another way to say it. And then maybe you can do a little exercise. Modify the code to create a set of all multiples of 3 less than 22. Should only take you a moment. Right, let's look at some other basic properties of sets. So sets are unordered. Unlike lists, like lists in Python, for example, sets do not have a defined order. So the set ABC is the same as the set BCA or CAB and so on. We can, of course, define an external ordering. We could define a program or a specification that would put elements of a set into a given order, but that's not what we're doing in creating a set per se, right? The sets do not have an order. As we've mentioned, each element occurs at most once in a set. So although you shouldn't often see a notation like the following, 1, 1, 1, the set of all set containing 1, 1, and 1, well, that's meaningless. It actually means the set of 1, right? Those other two ones are redundant. Now, if we want to allow multiple occurrences of the same element, we have a different data structure or a different mathematical construct that's called a multiset. That data structure is often also called a bag. It's unordered and it allows duplicates. So here's a summary of notation, one of which we've already introduced, but here's a bunch more that you'll need to be conversant with. So we have N, this funny script of the capital letter N, which means the set of positive integers. In our case, we're going to assume that that includes the number 0, so we really might call it the set of non-negative integers. We've seen in the MIU problem the vertical bars talking about the cardinality of a set. So the set 2, 3, 4 is a set with 3 elements, therefore the cardinality of that set is 3. We've introduced set membership with this funny E-like looking symbol. So X is an element of Y. We draw a line through it to say X is not an element of Y. Now we get finally to some new stuff, talking about sets, proper sets, and subsets. So X is a proper subset of Y, which means that everything that's in X is in Y, but they're not the same set. They're not equal. Which is then the next bullet here, we can say X is not a proper set of Y just by drawing a line through it. Then we also get to X is a subset of Y, which allows it to be equal. It's not a proper subset, it's a subset. And I like this notation because it has sort of what you might think of as half a little equal sign, as a line below the proper subset symbol. Very confusingly, this is quite unfortunate that people have used alternate notations in the literature. I think it's becoming more common because it is a bit clearer, at least in my opinion, to use this notion of set as this thing that looks kind of like a letter C, and rather proper subset to be the thing that looks like a letter C, and the proper subset with a line under it is then subset, right, that it could be equal. And then we can reverse the direction of this symbol, make the C face backwards, to say that X is a superset of Y, or in this case a superset or equal to Y. So I'll try to be consistent about this. There are some alternate notations. There's also this C with a line and a line through it underneath it, which means a subset that is not equal. But we're going to use just the C-looking character to mean that. This latter thing is a bit less common in the literature. Right, so this is a good cheat sheet to have. I'd recommend for students that are new to this topic, you might even print this out, put it up on your wall next to your computer as you go forward with this material. Right, so let's have a few other examples or exercises in Python. So just to show that sets are unordered and may contain duplicates, let's look at the first example. So ABC is equal to BCA, and we're using the curly brackets that Python has to denote sets, and it comes back with the answer true. And if we put in 1, 1, 1, then that Python will also know that that's equal to true as well. Right, and then try this little exercise, yet another trivial exercise, but just to gain this muscle memory. Is QSTS the same as, and I guess, sorry for the typo there, it should be a double equals, is the same as STQ. Let's talk a little bit about partial sets and multisets. So we've already just talked about the notion of a subset. Here, let me just drag the slide down a little bit so we can see it better. So set M is a subset of M2 if for all X in M, so all the elements of M1, X is also in M2. And we give it to this notation, as you see here, that it's a subset, although it could be equal. It's not a proper subset. A set M1 is equal to a set M2 if for all elements of M1, all those elements are also in M2, and vice versa. Right? If it's bidirectional, then we know in fact they're equal. Everything in M1 is in M2, and everything in M2 is in M1. Okay, so M1 equals to M2 is equal to M2 if and only if, that's the IFF symbol, if M1 is a subset of M2 and M2 is a subset of M1. Subset meaning subset or equal, not a proper subset. And just to highlight this additional bit of vocabulary or notation, if and only if is a common symbol, and it also has, instead of a letter symbol, it has a sort of graphical symbol of this bidirectional arrow. So keep that in your toolbox, if you will, because we'll need that as we come back to it. So it's an important part of many definitions, is saying something is true if and only if the following is true. It's a bidirectional relationship. And proper subset. So a set M1 is a proper subset of M2 if M1 is a subset of M2 and they are not equal. So a proper subset is a subset relation that excludes the case where both sets are equal. The opposite relation from subset is superset, and so we just reverse the direction of the symbol to say that. So M1 is a superset of M2 if M2 is a subset of M1. And here we're using this if and only if symbol, the bidirectional arrow. They're true going both directions. If M1 is a superset of M2, then M2 is a subset of M1. All right, and if we want to negate that relationship, we just draw a line through it. And again, there is this confusion. Sorry about that, but it just is what it is. People have used different notations over history, and so it's important for me to let you know that exists. And just be careful when you're reading things in the set theory literature that you understand what pattern of notation the authors are using. Okay, let's do another little exercise in Python. Python has the method is subset for the subset relation, and it uses the less than symbol for proper subset. So we can determine whether 357 is a subset of 2, 3, 5, 7, 11, 13, and indeed it's a subset, and it's also a proper subset. So as a little exercise, see if you can write the Python expression for asking is 2, 3, 4 a subset of the my set that's defined here. All right, we need to consider a few more things, and a confusing aspect to set theory is this notion of the empty set. I found it a little challenging myself and have gotten some things wrong over time, but I think I've gotten it straight now, and so I want to impart that experience to you as well. So this notion of the empty set can be denoted in several ways. Often it's a zero with a line through it, or it's just a set of curly brackets with nothing in between. And every set has a subset that is the empty set. So you can think of it as, let's say we have ABC as our set. The subsets of ABC include A and B. It includes just A, and so you can see we're sort of taking elements out of this set to form the subset. Well, you can take all the elements out of this set, and you still have something that's a subset. That's the empty set. Empty set is a subset of every set. Critically, however, it's not a member necessarily of every set, and you can think of that with the notation, right? You have this curly bracket notation of 2, 3, 4. If you take all the elements out, you haven't removed the empty set, you're merely left with the empty set. In order to have the empty set be a member, you'd have to have this zero notation, the zero slash empty set, comma 2, 3, 4. Then the empty set is a member of your set, because as you're going through pulling elements out of this set, one of those things you're going to grab is this empty set symbol, right? In that case, it's a member. So unless explicitly stated, the empty set is simply a subset of every set, not necessarily a member. All right, so let's do a little Python exercise. So we can have a variable that we define as empty. Empty equals the set with no members. So Python has alternate ways to talk about the empty set or define the empty set. And here's a case where you can call the set function with no members, and that gives you the empty set. So if we define another set called my set, that's 1, 2, 3, and we ask, is the empty set a subset of 1, 2, 3, we get the correct answer. Python tells us yes. So as an exercise, how would you write a function to test whether a set is not a proper subset of another set? Right, so give that a try. We've talked now about a number of important sets in mathematics, and here's just a rundown of what we've mentioned, plus a few new things. So we talked about the empty set, with notated as a zero with a slash, or just curly brackets with nothing in between them. The empty set is a subset of every set, every possible set, because you can always take out all the members of that set, and what are you left with? You're always left with the empty set. There's n, this set of natural numbers, and It's very fundamental, and computer scientists and modern mathematicians start counting from zero, so that's where we're going to stick with this course. If you look at really old literature, maybe 100 years old, there might be some confusion about that. We can also be very explicit in our notation. We could say n plus is strictly the positive integers, so not including 0, starts at 1, 2, 3, etc. We've got z, also in this similar unusual script, is the positive and negative integers, so it goes to negative infinity and positive infinity. We have q, the set of rational numbers, which means that for every possible element of the positive and negative integers in the numerator and every possible element of the positive integers being in the denominator, that combination, that ratio, is within the set Q, right? So this gives us everything from infinitesimally small things, that are negative. So if p is a very large number, a large negative number, maybe it's negative 1 million over a small q, then we get a very large negative number. We can also be very close to the zero by having say 1 for negative 1 for p, and q is a very large number, then it's a tiny fraction, very close to zero. If we have positive numbers for p, we can do the analogous thing of being either very close to zero or very far away from zero, and everything in between. We also have r, the real numbers, which includes all of q, all of the rational numbers, but it also includes irrational numbers like pi or the square root of 2. Right? So those are useful and common notations for some common things about numbers that you'll see in the literature. In Python, it's a dynamically typed language. It's a little less strict than some statically typed languages like C++ or Java, or I believe Rust also, although I need to learn Rust myself. And as a dynamically typed language, we don't always know what something is. We get a different format when we print out the results of these expressions sometimes than when we're defining them. So here's just an example. So let's say my int is equal to the int of 2. We print that out, we get just 2. If we have the my float is equal to float of 4, when we print it out, we've said it's a float, therefore as a pretty print string from Python, it gets the decimal and a 0 after it. All right, so now a slightly bigger exercise. Try to give formal descriptions of the following sets. All even numbers, all square numbers, and all prime numbers. And once you've done that in mathematical notation, try to do that looking back at, to the beginning of this slide deck. We had a notation for giving a description of a set. That'll give you the notation that you should be using. See if you can find that and try it yourself. And then try to create Python code that tests whether a number is within each of these sets. Right, that's the last slide in this lecture, and as you can see, we'll go on next to constructing natural numbers and term algebra. Try all the exercises, put them all together, and if you can do them all, you've thoroughly learned this material, and you're ready for the next set. So see you in the next video.